Okay, everyone. Yeah, we're going to have a talk now from David MacIver, and it's on easy solutions to hard problems.
Thank you very much. The URL there, all the slides are online, and also post a link later. And one of the reasons why this is important is that there's going to be lots of code examples in this talk, but you don't need to worry about reading every detail of those and understanding exactly what they're doing, because you can check this out later, and I'll explain the sort of most important points as I go. I am David MacIver. I'm available online in various forums. I normally work on a testing tool called Hypothesis, which this talk is not about because I was really bored of giving talks about it. But if you want to actually see a talk about Hypothesis, then Alex is giving one after lunch, and I am also running a workshop on it tomorrow. And that's the last thing I will say on that subject. One thing I do want to say as a disclaimer in advance, which is that I wrote this talk entirely before coming to the conference, and there is an example later that will make it look like I'm giving the conference organizers a hard time, and I'm really not. So let's just do a quick round of applause for the conference organizers, who are doing a great job. You'll see what I mean with that later. First, I actually want to talk about problems that are in NP, and sort of about NP hard problems. People tend to think that NP means difficult. And this sort of is understandable given the associations, but actually NP means easy. And I don't mean that as a pun. NP is a particular type of problem that is really just on the cusp between easy and difficult, because it may not be easy to solve, but once you have a solution, it's easy to verify what that solution is. NP means non-deterministic polynomial, and what that means is that you can imagine trying all of the solutions in parallel, which will need a lot more than the 64 cores that Sarah gave us earlier. And one of those things will come up with an answer if there is an answer. So these tend to be search problems, where you're asking, does a solution to this problem exist? And then the answer is either yes or no. But usually what we actually want is that solution. But in a formal sense, we're just really asking the yes or no question. And the canonical example of a problem that is in NP is the Boolean satisfiability problem, called SAT for short. And what this is we've got a bunch of Boolean expressions that are all just a list of ORed together variables or the negation of those variables. And we want to know if there is some assignment that makes all of these expressions true at once. So this is how it might look in Python. You've got an all expression over these list of clauses, and each one of these is in one of these simple forms. And we want at the end to get an assignment of what these variables are that can make all of these things true. And SAT is canonical NP problem in the sense that if you can solve SAT well, then you can actually solve any other problem that's in NP well as well. Also, I'm not going to prove that to you. I don't actually understand the proof, but it is true, honest. And this is also an example of what I was saying earlier. Technically, SAT is the question: are all of these simultaneously satisfiable? But that's about as interesting as asking someone, can you solve this problem? And they say, yes, I can. And you're like, thanks. So you do actually want these solutions as well. I'm not going to be talking about SAT today, but SAT is the thing to bear in mind when you're thinking about NP problems and NP hard problems. What I'm going to be talking about is integer linear programming. I think the abstract says I'm talking about mixed integer linear programming, but I'm actually not. It'll just be integer linear programming. Mixed is when some things have to be integers and some don't. So the core idea of linear programming is that you've got the same sort of thing as SAT. You have a bunch of linear constraints, which means you've got sort of weighted sums, and these must be equal to something, or this must be less than or equal to something, inequalities like that. And in integer linear programming, the big thing is that you can make all of your variables, or have to be integers rather than floating point real numbers. And continuous linear programming is easy, but integer linear programming is just as hard as SAT, because as you can see from this sort of translation of the previous example, you've got three variables which were previously booleans and are now integers, which we've constrained to be between 0 and 1. In Python, those are actually equal to the booleans, but let's pretend that's not true. It's terrible. But we've got an encoding of the booleans as false as 0, true as 1, as you normally would. And so the first three constraints are just restricting the value range of our variables, and the latter are a translation. So 1 minus a variable is the same as its negation because it maps 1 to 0 and 0 to 1. And when you're adding things together, if any of them are 1, then the result will be greater than or equal to 1. So that's how you can translate the ORs. And you can mechanically do this for any SAT problem in almost exactly the same way. And you can feed this then into a solver for integer linear programming. And this is sort of one of the reasons why this is a useful thing to know about, as opposed to just another way of looking at the problem, is that there are very good integer linear programming solvers that we can use. There are also very good SAT solvers that we can use, but integer linear programming is a lot more flexible and is a lot easier to tune to the sort of things we might want to do. There's a very nice Python library called Pulp, Python linear programming, which we can use to express an integer linear program in Python. And what it is, we create some variables with the Pulp type, variable type. They have to have a category, which can be either integer or continuous. In this case, it's binary, which just means integer. That's either 0 or 1. It's just a shorthand. Then we add these constraints, and we ask it to solve the problem, and we get the values out. And these are the values. You might notice these are not the same values as we had previously. One of the things about this sort of search problem is that there's generally not a single unique solution, and we're just asking for any one of them. And this is sort of a fairly direct translation of what we had earlier. And that's nice and all, but this is still a relatively abstract problem. And we can use this to solve more concrete things. And in particular, we can use it to solve all sorts of interesting planning problems because of the other big feature of integer linear programming, which is that you don't just have constraints, you can also ask it to optimize for things. So this is a planning problem called the knapsack packing problem. And what the idea is, I've got all this cool loot, and I've got this small backpack. And what can I do to put the maximum value of loot in my backpack in order to and get away with it? So you've got, more concretely, you've got a bunch of items. Each item has a weight and a value, and you've got a maximum capacity you can carry. So the problem is, how do we pick items that sum to less than or equal to my capacity that maximize the value? And this translates fairly directly to an integer linear program. What we do is we create a variable for each item, which says, do I want to include this in my backpack? And the total weight included is just the weighted sum of those variables, because the contribution of an item to my backpack is its weight if the variable is 1, or 0 if the variable is 0, so it's just the weight times the variable. So that gives us our constraint here. Trying to do that inverted is hard, so I'm not going to try that again. But we add the single constraint, which is the weight, and then we also ask it to optimize for this objective function, which is the same thing but for the value instead of the weight. And then we ask it to solve it, and we just return the items for which the inclusion variable is true. And this is a relatively classic planning problem. There is actually a better algorithm for it than using the integer linear programming, but the integer linear programming solution tends to run quite fast and is quite easy to write in comparison. Because one of the big things about integer linear programming, and one of its big advantages, is that even when there are specialized solutions that you could use instead, it tends to work as well or often better because lots of smarts went into writing these things that you're probably not going to have time to replicate when writing for yourself. And additionally, it's incredibly flexible, which means that you can use it for more general planning problems. Because often when we encounter an NP-hard problem in practice, it doesn't look exactly like one of the classic ones. You've got sort of some detail that is different or something that some reason you can't use the standard solution, and you don't really want to have to reinvent clever algorithms from scratch. So one example where this came up recently is scheduling a conference. The electromagnetic field conference that happened in Guildford recently, or near Guildford, was actually scheduled using integer linear programming. I wrote a prototype for it about 2 hours before getting on a plane and sort of threw it over to the wall and said, like, here, I haven't run it, but I think it works. It didn't work, but Jonty and Sam very capably turned it into a useful working program that did a pretty good job of the scheduling. There are a bunch of things we would do differently in retrospect, but it worked quite well. And one of the things that, like, the main benefit of my terrible prototype was that it took integer linear programming and made it not scary for them to work on, because this is just programming. Oh, sorry, a thing I've meant to mention earlier. It's called integer linear programming, but programming doesn't mean what we would call programming. It comes from those terrible mathematicians who work in operations research, hi Vince, because classically a program is another word meaning a plan. So even though we are writing programs to do integer linear programming, these are not the same word. But yes, this is a simple matter of programming, and I want to sort of get you to the same level of not being scared by this and just seeing that this is a thing you can use to solve your real problems, and it will probably do a better job than ad hoc things. So yeah, to schedule a conference, we've got a slightly simplified model here. The actual one we used was a little more complicated, but we've got time slots, we've got rooms, and we've got talks. And a room is in a time slot, sorry, a talk is in a time slot and a room. And so we create the same sort of inclusion variables that we had earlier, which is for each triple of room, talk, and time slot, we have a Boolean 0, 1 integer variable. It's 1 if the talk is in that room at that time, and 0 otherwise. Then we ask it to solve it, and we just return a set of triples at the end. Right now, what will happen is it will probably put all of the talks in the same room and same time slot, which doesn't work very well. Which is why we've got these little to-dos in the middle, which says, constraints go here, optimize me. I'm sure we've all written code that looks like that. But the constraints aren't too bad, fortunately. So this is our first set of constraints, which is that every talk must only be scheduled once, and it must be scheduled exactly once. And so we create one constraint for each talk, which then just adds up its appearances in every room and every time slot, and says this must sum up to 1, because the number of times it's scheduled is going to be the total count of the slots in which it's scheduled in, which are 1 where it's scheduled and 0 otherwise. So that will not actually solve the problem, because I forgot to mention the other thing it could do, which is that it could schedule every talk in every time slot in every room, which is another failure mode we wanted to avoid. But this is our non-conflicting constraint, which is that for every room in every slot, the number of talks in it must be less than or equal to 1. It could be 0. There could be gaps in the schedule, which we will largely try to avoid, but it does happen. But it can't be greater than 1. And this will work. We now have a perfectly valid scheduling system. It won't do anything interesting. It will just shove them all in a row in whatever rooms it finds, but that will work. It will at least do as well as the silly, greedy algorithm we could have written in 5 minutes. But the nice thing is that when things get more complicated, we can add more rules and it'll keep doing the same thing. So for example, some speakers won't be available on each day. So you might need to block out some room combinations or speaker combinations. So if we check whether a speaker is available in a particular slot, we can just add a constraint that says this variable must be equal to 0 if they are not, and the scheduling system can just then be rerun and work around it. And this was actually one of the big benefits for EMF, was that they could just make changes to the schedule and have the system work it out automatically. Because previously, when they were doing everything manually, it was okay the first time, but by the time the 10th speaker had told them that this slot didn't work for them, or someone new came in, or someone dropped out, they were about ready to tear their hair out. And this sort of flexibility and planning really helped. The other thing that can happen is that some people are speaking in multiple talks, and you don't want to schedule them against themselves. That doesn't go down very well. So what you can do is you can have sets of talks by speaker, and you can say that in any given time slot, the number of talks by that speaker must be less than or equal to 1. And this constraint works more or less the same as our previous constraints of with a lack of conflict, but it's summed over more rooms. They both count conflict in room or in time in these cases. And here's the bit where I'm not giving the organizers a hard time, which is, suppose we've got our constraints and it will produce a perfectly valid schedule, but we do want to make advantage of the optimization thing to cause it to give us a really good plan. So what we want to do is, suppose we knew in advance how many people wanted to attend a given talk and what the capacity of any given room was. Then what we can do is we can use quite a nice trick, which is to introduce some auxiliary variables where we don't actually care about their values and that they're required to express the problem. So each talk will have a certain number of people who are disappointed because they can't make it into the talk because the room is over capacity. And we want to try and optimize to minimize the total amount of disappointment. And the way we do this is, first of all, we calculate a capacity for a talk, which is just the capacity of the room it's in. So it's a weighted sum of the room capacities times whether it's in that room or not, because if the value is 1 for being in a particular room, then that's its capacity. If the value is 0, it's not. It doesn't add anything to the sum. And the number of people who are disappointed isn't just the capacity minus the number of people who are the number of people who are interested minus the capacity, because if that were the case, you would potentially get a negative number of people disappointed, and people don't work like that. You don't get some people who are really excited because there were 30 free slots in a room, which is why we introduced this auxiliary variable, and it's an integer number of people, which is always greater than or equal to 0, and is always greater than or equal to this difference. So if a negative number of people would be disappointed, then it's capped down below at 0, but otherwise it's greater than or equal to the capacity that would have been filled but couldn't be. And one thing about this is that these disappointment variables are actually an overestimate. In the constraints, there's nothing stopping us having 1,000 people to be disappointed, even though only 2 people couldn't get into a room and only 500 people actually attended our conference. But because we're minimizing, that doesn't matter, because the first thing it will do is it will shrink the variable down until it's tight. And yeah, so we create all these disappointment variables once for each talk, and then we add them up, and we ask the planner to optimize for that, and it will give us a great plan that puts everything in rooms with the right capacity. I'm happy to talk to organizers about this if they want to do this next year. And then there was another great trick that we figured out with when planning EMF, which is that you only really want to use that for the first one, because otherwise, every time a change happens to the schedule or a new constraint is added in, the planner might just completely rearrange everything, and then you've got speakers going, I don't understand, I was speaking on Sunday, why am I now speaking on Thursday? And sometimes that happens, but you don't want to do it unless you really need to. So what we did was that future runs of it, what we actually optimized for is similarity to the previous schedule. So we make the smallest number of changes that are required to fit into the new constraints. And this turned out to actually have a really nice effect of speeding up the process a lot as well, because it meant that you were looking very near a correct solution when trying to plan things. So I think it was about half an hour for the first run on EMF, and about 15 seconds for subsequent runs. Those numbers may not be right, but they're sort of the right order of magnitude. And you could also combine these. You could do like a weighted sum where one rearrangement is equivalent to 10 disappointed people or something, but we didn't look into that very much. I'll just briefly mention some of the tools that you can use to do this sort of thing. There's Pulp, which I've been showing you today. Pulp is lovely in almost every regard except for performance. It's great for prototyping, and often the prototype is more than good enough to run in production. Sometimes I've found that because it spends a lot of time in Python building up the problem it's handing over to the solver, and sometimes that ends up dominating. But most of the time, the flexibility and the ease of use wins out over that problem. There's GLPK, which is the GNU Linear Programming Kit, which is an LGPL open linear programming solver, and works really well, and is the backend I was using in these examples. There's CoinOR, which I can never remember what it stands for, but it's something very clever and funny, I'm sure, which is a general project with lots of sort of a Swiss Army knife for operations research and things like this, and is actually the project that Pulp comes out of. I've never quite figured out how to use their tools directly, but Pulp is a good interface to them. There's also Cplex, which you will probably not need to use, but it's worth bearing in mind this exists. It's IBM's integer linear programming solver. It's incredibly powerful and incredibly expensive. This is sort of one downside of this sort of tool, which is that although the open source tools are very good and probably more than good enough for anything you need to do with this, the proprietary tools are a lot better because they've had a lot of time and money sunk into them. So that's more of a thing to bear in mind if you end up running this sort of stuff in production and you are running into the constraints of the solvers, but it shouldn't stop you from using the open source ones for all your day-to-day use. And that's pretty much all I have to say. Thank you very much.
Thank you, David. Thank you very much. So I don't know if you're...
I'm perfectly happy to take questions. Yep.
Yeah, and we've got lunch after this, so I mean, if we...
Sure,
if
I'm in a hurry.
Yeah, so are there any questions for David?
Hi, thank you, very interesting talk. I guess my question is a bit of a boring one in some ways, but the problem I always find when I'm trying to do something clever like this is actually getting the data in and out at the beginning and the end without that taking over the programming aspect of the project. You can do your solver in 50 lines of code or something, but playing around with it to try and get all of your data in and get it out in a format that can then go into a talk schedule online or on paper or whatever. I just wondered how you dealt with that in this particular example.
Data munging is always hard. I think in the particular example for EMF, they had all of the data just in a Postgres database, so just ended up writing a bunch of boring ORM or SQL code that set up the problem from that. And I think that's going to be different for every problem, though. Like if you've got stuff in CSV, you can use a CSV importer. If you've got it in a database, But there's no particular support in that for pulp. It's just write a program to read in the data and create the constraints off the back of that.
Yep, cool. Thank you.
There's another one here.
You might have mentioned this earlier, but maybe I wasn't listening properly. Do all NP problems reduce to ILP, or are there other base problems that they sometimes reduce to?
So there's the notion of a problem being NP complete, which SAT is, and what that means is that any problem that is in NP you can reduce to SAT. And as we saw earlier, you can reduce any SAT problem to an integer linear programming problem. So by transitivity, you can reduce any problem that's in NP to integer linear programming. The reduction may not always be particularly natural. Like, I've seen the reduction for traveling salesman problems multiple times, and I still can't do it from memory because it's got some very weird tricks in it, but it's always possible.
Tried to look at the documentation myself, but so Pulp has got interfaces to all the solvers you listed.
Yep.
If you don't have those solvers, does it have its own written solver in Pulp itself?
Yep.
So you need to get like
you need an external solver to use it.
Cool. So what Pulp does is it
Yep.
builds the problem, passes
Yep.
it to a solver.
Pulp is an interface to solvers. It's not a solver in its own right.
Which one did you use?
I use GLPK.
Cool.
I used to use LPsolve because it's much more user-friendly, but it's unfortunately very unmaintained. So I've switched over to GLPK, which is largely a good replacement.
Hi, just out of interest, is this being used for sort of general project planning, sort of Gantt-style munging? I can imagine it being useful for that.
I'm sure it has been used for that. A lot of where this theory for this came out is from things like management science, so it would be very surprising if they weren't using it for that sort of thing. I don't know of any particularly good examples of people using it for that, but that may be more my lack of familiarity with management science in general than it is with there being a lack of good examples.
Any more questions? I have one as well.
Okay.
I just wondered, how did you get into this particular line of these problems? Have you got a background?
Okay. No, so my original reason for getting into this is because I've got a sideline interest in voting theory, and there is a voting system that manages to be very NP hard to solve, and some of the best solutions for it end up reducing it to integer linear programming. And it's to do with trying to find an ordering which minimizes the total sort of disappointment in terms of people would prefer this candidate to that candidate. But it doesn't work very well, so I mostly don't use that.
Oh, no, there is one more question at the back. Sorry about that.
Hi. So you mentioned that this was time-consuming the first time, and I was wondering if at what point does it start to become interesting to do this with a computer? Because one very similar problem that I used to solve a lot when I was a kid was I had this 90-minute tape, and I was trying to fit songs on both sides, and yeah, it usually took me about 15 minutes or so to figure out which song I wanted on each side to maximize the number of songs on the tape. And so when you say it takes 30 minutes to calculate the schedule for a conference, I'm wondering if it wouldn't be, you take that into account plus the time to write the program, at what point does it become interesting to actually do it with a computer?
So the thing to bear in mind with that 30 minutes is that EMF had a lot of talks and a lot of slots. So doing it by hand was significantly more time consuming than 30 minutes. And also most integer linear programming wouldn't take 30 minutes to run. Like 30 minutes is longer than anything I've actually encountered when using it myself. And it will also probably get a better solution than you did by hand because it can guarantee optimality rather than you doing it by hand usually ends up being a greedy solution where you just essentially find a local optimum rather than a perfect one. But yeah, there are absolutely some things where it would be overkill to apply this. But particularly for conference scheduling, where you're likely to want to rerun it over and over again as things change, it's sort of in that benefit of automation, because even when doing it once is slower, doing it twice or 3 times suddenly becomes much faster. Certainly, Jonty was ecstatic about the experience of using this versus having done it manually previously.
Okay, I think we've probably got time for one more. Is that right, David? Okay.
I'm happy to stick around as long as people have questions, to be honest.
This is just a quick one. David, are you volunteering to write next year's schedule?
I'm volunteering to throw you a little prototype and say, I think it works.
Okay, excellent. I think if there are more questions, it's probably best if they come to the front so that we can then
Sure thing.
people
Yep.
head to lunch. Thank you very much.